Today we're going to talk about algorithm analysis. And these are what we're going to talk about today. First, I'm going to introduce what algorithm analysis is, and I'm going to give you a real world example. And then we're going to have a look at theoretical analysis, how we theoretically analyze algorithms. And I'm going to introduce the master theorem. And then I'm going to summarize this lecture. All right, first, introduction. What is an algorithm? An algorithm is, in general, a finite set of well-defined instructions that take some set of values as input and produces some set of values as output. And why do we do this? To solve a problem. So an algorithm is to solve a problem, and it receives a set of values as input and then produces some outputs. And in computer science, and what we are doing is computer science, right? A sequence of computational steps that transform the given input into the output for a given problem is what an algorithm is about, all right? So here, a well-defined instruction is here, computational steps, because we are dealing with computers. And why do we care about algorithms? Why do we study algorithms? Suppose that our computers are infinitely fast, and our computer can store infinitely many things, meaning that our computer has infinite memory spaces. Even in these cases, do we still need to study algorithms? The answer is yes. The reason is we would still like to demonstrate that our solution terminates. Even though our computers are infinitely fast, if it doesn't terminate, then our algorithm would not come up with the right solution. So we need to analyze our algorithm if it is going to terminate and produce the right, correct answers. And this is the second reason. We want to know that if our algorithm is going to produce the correct answer. So these are some reasons why we study algorithms. So basically, because our computers are not infinitely fast, so we want to find out some efficient algorithms, and that does not spend much memory spaces. So basically, we want to make efficient algorithms because our computers are not infinitely fast or have infinitely memory spaces. Now, of course, computers are not infinitely fast and do not have infinite memory spaces. And computing time is a bounded resource. So is space in memory. And we need to use these resources wisely or efficiently. That is the goal of studying algorithm analysis. And among several algorithms, we would like to choose the most efficient algorithm. Of course, we want to do this. And this process, choosing the most efficient algorithm, is called algorithm analysis. Basically, we are predicting the resources, space or time. So there are two types of complexities we are going to analyze. The first one is time complexity. And the second one is space complexity. However, among these two things, we basically or mostly concentrate on time complexity. So we focus on time complexity more than space complexity. Because in general, space might not be a big problem, but time becomes a big problem in most cases. So that is why we focus on time complexity rather than space complexity. All right, so that was the introduction. And from now on, I am going to give you a real world example. So here we're going to have a look at a problem. I'm going to describe this problem. What we are going to discuss is maximum contiguous subsequent subproblem. So what is this problem is about? First, we are given, so this is going to be our input, an array with integers. So we have n integers, array of n integers. And what we want to do is find, and this is going to be our output, find the maximum values of subsum. This is called subsequent sum over all possible choices of I and j. So this is summing some part of consecutive numbers. So k starts from I and ends at j. And we want to sum these numbers. So I'm going to give you one example. For example, if the input sequence is -2, 11, -4, 13, -5, 2, the answer is 20, because these three numbers in sequence produces the maximum subsequent sum. All right? So does everybody understand this problem formulation? If you can understand, please ask me your question. So this is our problem we're going to solve as an example. And we can come up with a naive solution. That is, you just naively check all possible choices of I and j. So we check all combinations of I and j and evaluate the subsequent sum. And among all those possible choices, we choose the maximum value. And how many subsequences do we need to check? How many subsequences are there? This is quite easy. The answer is we need to choose two numbers, I and j, between 1 and n. So that is this one, choosing two numbers, I and j. And this n corresponds to just single number. So if we say A1 is the maximum subsequence sum, that means I and j are both 1. So we are choosing just one number. So this corresponds to n combination 1. So if you sum these two numbers, it's going to be n squared over 2 plus n over 2. So this is all possible subsequences. All right. Now let's implement our naive solution together. So up to this point, are there any questions? All right, let's move on. So we are going to implement our naive solution. So let's say def max sum naive, and we are receiving an array. Let's call this array A simply. And we're going to define some variables to keep track of the maximum sum. And this is going to be our I, start and end. This is going to be our j. And what we are going to do is we're going to iterate through the length of A. So I becomes 1 and 0 through n minus 1, right? And we also need to iterate J. However, we are going to iterate J from I to the end of the sequence. So J is basically from I to the end of the sequence like this, all right? And what we are going to do is we're going to check the current subsum. So how can you evaluate the current subsum? We define another variable k, which changes from I to j plus 1. Then we're going to sum the subsequences to this sum variable. Okay? So if this sum is larger than max sum, we are going to assign sum to this max sum because this current sum is the maximum value of the subsequent sum, and start is going to be current I, and end is going to be current j. Okay? So we iterate I and j over all possible cases, and then for those all possible cases, we sum, evaluate. So this for loop is to evaluate the subsum for current I and j, right? And then we check or update our track. So we are keeping track of the maximum subsum and the start and end value, all right? And after we check all possible cases, we return the max sum and start value and the end value. So this is how we implement our naive solution, all right? Okay, let's get back to our slide. And let's analyze our naive solution. So what did he just do? To analyze our solution, what we are going to do is, rather than checking all possible operations, we'll only count the number of additions. So we are not going to care about like looping through A, I, and J. We do not care about these operations. We only count the number of additions because this operation takes the most of the time, and this assigning operations does not take much time. So this one is the major one. So we only take care about the addition, all right? So how many times do we add or call this expression? That is expressed in this equation. We iterate I from 0 to n minus 1. And I told you that j here goes from I to n minus 1. So j here goes from I to n minus 1. And the number of addition here is j plus 1 minus I. That is expressed here. So this is the number of additions in this algorithm, our function. All right? And how can you evaluate this? When we expand this one or put j I here, then this value changes from 1 to n minus I. All right? And we know how to evaluate this expression, right? That is, we know 1, 2. If you want to sum from 1 to n, that is n times n plus 1 over 2, right? So we're just doing the same thing. N minus I plus 1 times n minus I over 2. And when we expand this one, here we are substituting n minus I as k. So n minus I becomes k. Then k changes from 1 to n, right? So we are substituting n minus I as k. And because I changes from 0 to n minus 1, if we put these two numbers here, then we know that k changes from n to 1. So we are just reversing the order of addition, and then we can say k changes from 1 to n, right? And when we expand this one is going to be k squared plus k. And we know that from high school mathematics that summing these k squared corresponds to this one, and k becomes this one, right? And because we have division by 2, that comes here, right? So when we expand this one once again, then it becomes n cubed plus 2n squared plus 4n over 6. So this is the number of additions that this function is conducting. All right, so this is how we analyze our algorithm. Any questions about analyzing this function in this way? So there was one question: what is the n in this equation? Here, n is the length of this array. So here, n is the length of the input array. Any other questions? All right, let's move on. And how can we improve our naive solution? Are there any suggestions? How can we improve our naive solution? This one is, of course, not the optimal one. Not optimal. Any suggestions to upgrade our algorithm? Okay, I'll give you 30 more seconds to think about how to improve our naive solution, and then we're going to discuss how we can approach this solution. All right, let's talk about how we can improve this algorithm together. The subsum from I to j, this one, can be obtained from the subsum from I to j minus 1 with only one addition. So what I mean by this is subsum from I to j can be regarded as subsum of I to j minus 1 plus aj. All right. So you can make this part more efficient. So this is our first PPP exercise. Try to implement the faster version